Now, we discuss the use case workflow at a glance of AI. First, we access and load the data. Second, pre-process the data. Third, derive features using the pre-processed data. Fourth, train models using features derived in the previous step. Fifth, iterate to find the best model. And finally, integrate the best trained model into a production system. For us to better understand the workflow, we will try to use a specific use case, which is a health monitoring mobile application. So the training a model to classify a physical activity in a health monitoring app will be a very good example for us to better understand each of the steps in our machine learning workflow. Now, in the case of a phone or mobile health monitoring app, we have the following inputs consist of 3 axial sensor data from the phone's accelerometer and gyroscope. The responses, or basically our output, are the following: walking, standing, running, climbing stairs, or lying down. So basically, we have now an idea of what would be our dataset structure. So first, for the input features, we have the values from the accelerometer and the gyroscope, while on the other hand, our output label includes activities performed, such as walking, standing, running, climbing stairs, and lying down. We want to use the input data to train a classification model to identify these activities performed by the person. Our goal is classification, correct? Therefore, we will be using supervised learning. So the trained model or classifier will be integrated into an application to help users track their activity levels throughout the day. The first step is to collect and load the data. Now, as mentioned earlier, the data will be coming from 2 types of sensors, particularly or specifically accelerometer and gyroscope. Now, for us to be able to acquire the data, we need to do the following. So, first, the sit down holding the phone position, we logged the data from the phone and label it as sitting. Second, stand up holding the phone. In that case, we log the data and label it as standing. We repeat the whole process until we achieve our desirable number of samples or instances. The available censored or labeled data can be in a form of a text file or CSV file. Now, machine learning algorithms aren't smart enough to tell the difference between noise and valuable information. Before using the data for training, we need to make sure it's clean and complete. That leads us to the second step of our workflow, which is the pre-processing of our data set. It is very important as it affects the accuracy of the prediction of the model. We import the data into our simulation or software platform. In this case, it can be MATLAB. Now, to pre-process the data, we do the following. Look for outliers or data points that lie outside the rest of the data. We must decide whether the outliers can be ignored or whether they indicate a phenomenon that the model should account for. In our example, they can safely be ignored, as it turns out that we move unintentionally while recording the data. Again, it's very important to remove these outliers as they will significantly affect the accuracy performance of the model. The second step is to check for missing values. Missing values can happen if there is an error in sensor data collection. Maybe perhaps lost data due to connection dropped during recording. We could simply ignore the missing values, but this will reduce the size of the data set. Alternatively, we could actually substitute approximation for the missing values. We call it interpolation or using comparable data for another sample. Another term we use is data imputation. Third is to remove gravitational effects from the accelerometer data so that our algorithm will focus on the movement of the subject and not on the movement of the phone. Because at the end of the day, we were trying to monitor the physical activity of the human. Lastly, divide the data into two sets. We save part of the data for testing. We call it testing data set. And the other part, we use it for training. And we call it training data set. This is referred to as holdout and is useful for cross-validation technique. Now, if you will ask how many should be allocated for testing dataset and how many should be allocated to training dataset, as a rule of thumb and the most commonly used splitting percentage, for the testing dataset, it should be 20% of your whole dataset, while for training dataset, it has to be 80% of your whole dataset. But ideally, the training dataset should be larger than the testing data set. We now proceed to the next step, deriving features. We also refer to this step as feature engineering or feature instruction, which is actually another important workflow process of machine learning. It turns raw data into information that a machine learning can use. For example, in Activity Tracker, we want to extract features that capture the frequency content of the accelerometer data. These features will help the algorithm distinguish between walking, which corresponds to the low frequency, and running, which corresponds to the high frequency. We then create a new table that includes the selected features. Use feature selection if we have the following situation. If we want to improve the accuracy of machine learning algorithm, or boost model performance for high-dimensional dataset, improve model interpretability, or even in preventing overfitting. Now, the number of features that you could derive is limited only by your imagination. However, there are a lot of techniques commonly used for different types of data. So we have here 3 commonly used feature engineering processes depending on the data type. If we have a sensor data, such as in our example, we can actually use feature selection tasks such as peak analysis, pulse and transition metrics, and spectral measurements. Now, if we have a data which is in a form of image and video, we can use the feature selection task, extract features from edge locations, resolutions, and color. The following techniques we can use to perform such tasks, such as bag of visual words, histogram of oriented gradients or HOG, minimum eigenvalue algorithm, and edge detection. Finally, transactional data. For this type of data, we can actually calculate derived values that enhance the information in the data. Such techniques that we can use as feature engineering are timestamp decomposition and aggregate value calculations. We now move on to step number 4, where we start building and training our models using various types of machine learning algorithms. When building a model, it's a good idea to start with something simple. it will be faster to run and easier to interpret. Now, amongst the available machine learning algorithm, one good example, which is simple in concept and in structure, is the decision tree algorithm. We try to use decision tree algorithm for us to be able to build a model that will classify the activity performed by the human given the input features obtained from sensor dataset, accelerometer, and gyrometer. Now, to see how well it performs, we normally use a confusion matrix. A confusion matrix is the representation of all true classes and predicted classes, meaning how many of the samples were correctly classified and how many of the samples were incorrectly classified. Now, the confusion matrix is actually a good visualization for us to better evaluate and understand the performance of our machine learning model, as it basically represents various classification metrics such as accuracy, precision, recall, and F1 score. Now, the confusion matrix shows that our model is having trouble distinguishing between dancing and running, such as in the example of our use case. Why is that so? We can see in our confusion matrix, specifically for dancing and running, that it only achieved 59%. What does it mean? It means that dancing as a class was only predicted correctly 59% of the time. Similarly, for running, it was only predicted correctly 93% at a time. So basically, compared to other output labels, which are sitting, standing, and walking, which achieve 99 or greater than 99%, the other two output labels, running and dancing, achieve a very low accuracy performance. Maybe a decision tree doesn't work for this type of data. Therefore, we'll try to use a different algorithm. This time, we use a more sophisticated one, which is the KNN, or the K nearest neighbor. It is another simple algorithm that stores all the training data, compares new points to the training data, and returns the most frequent class of the K nearest point. Basically, it uses the distance formula to calculate the number of nearest points depending on the given K value. Now, after building the model using the same dataset for KNN, we achieve this confusion matrix wherein we will notice here that running and dancing significantly increases their respective accuracy in comparison with the use of a decision tree algorithm. So, from 59% using decision tree, it basically increases to 92% using KNN. That is a huge difference if we are going to compare the performance of the two models. However, KNN takes a considerable amount of memory to run, since they require all the training data to make a prediction. This is where the trade-off comes in. As we mentioned earlier, there is a trade-off between the speed of classifying the prediction and the accuracy of prediction. Now, we try a linear discriminant model, but that doesn't improve the result. Finally, we try a new one, this time support vector machine, and rebuild our model using the same dataset. Now, getting into the confusion matrix result for SBM modeling, we can see in our confusion matrix that from 92% performance using KNN, the accuracy increases to 96% for dancing by using the SVM. Hence, we achieve our goal by iterating on the model and trying different algorithms. Again, it is a trial and error process. If our classifier still couldn't reliably differentiate between dancing and running, we'd try to look into ways to improve our models. One of them would be to train several models and compare them, or it can also be going back to the pre-processing part, particularly the data imputation, data cleaning, or even in feature engineering or feature selection. Now, if we achieve such accuracy and that we are not satisfied, we can then further improve our model. There are a lot of ways on how we can do it. First, in a correlation matrix, it shows the relationship between variables so that variables or features that are not highly correlated can be removed. Second technique would be to apply principal component analysis, which basically eliminates the redundancy by finding a combination of features that captures key distinctions between the original features and brings out strong patterns in the dataset. Third technique that we can use to further improve our model is the sequential feature reduction process. These process involve reducing features iteratively on the model until there is no improvement in the performance. These are just some of the possible feature reduction techniques that we can use, but if we want to further advance our model and make sure that it performs the optimal performance based on accuracy, then we might want to further perform the following. Pruning branches from a decision tree if we are to use decision tree algorithm, or removing learners from an ensemble method. Ensemble method is actually the combination of different machine learning models, and from these combination of different machine learning models, we try to perform a voting process to identify which of the models achieve the highest accuracy performance. A good model includes only the features with the most predictive power. A simple model that generalizes well is better than a complex model that may not generalize or train well to new data. It is very important that the model was able to achieve a very accurate performance, but at the same time was able to converge or generalize our dataset. In machine learning, as in many other computational processes, simplifying the model makes it easier to understand, more robust, and more computationally efficient. And please don't forget that. Again, having a very simple model makes it easier to understand. Further improving our model, we can perform overgeneralization by fine-tuning, such as the use of model combination. These merge multiple simpler models into a larger model that is better able to represent the trends in the data than any of the simpler models could on their own. Another is to add more data sources. Look at the gyroscope data as well as the accelerometer data. Gyroscope records the orientation of the cell phone or mobile phone during activity, and this data might provide unique signatures for the different activities. For example, it can be a combination of accelerometer and rotations that unique to running. Once we've adjusted the model, we validate its performance on the test data that we set aside during the pre-processing, or we also refer to it as our testing or validation data set. If the model can reliably classify activities on the test data, we're ready to move it to the phone and start tracking.